Okay, well, hello everyone, and welcome to Hope 2014, which I think is the third Hope workshop. As we all know, effects are really interesting and also very challenging. So when I was a new graduate student, my advisor told me, okay, there are 4 difficult things in programming languages: higher order functions, state, polymorphism, and concurrency. If you look at 2 of them, you'll have a good thesis. If you look at 3 of them, you'll have a great thesis. And if you look at 4 of them, you won't graduate. But over the last few years, like, an immense amount of progress has been made on dealing with effects. And people in this room have made many of the contributions to dealing with this. And this is sort of especially timely since ideas from functional programming and other sorts of higher-order programming have really hit the mainstream now. So, later today we might see how we'll think about cache effects in Haskell programs. And for our keynote talk, Philippa Gardner will tell us about her work on verifying JavaScript programs. And I mean, if you've done any JavaScript programming, like the very idea of verifying a JavaScript program seems astounding, and yet with the sorts of things we've done, it now seems quite possible. So please take it away.
So hello everybody. Lovely to see many friends. It's great to be here. So this workshop is dedicated to John Reynolds, his supervisor. And I have heard over the years many talks where John has been absolutely fabulous and sort of pushed the boat as to what is possible to say for that talk. And I don't know, I couldn't possibly be that sort of fabulous, not John Reynolds fabulous, but I am pushing the boat here in terms of where we're at. So this isn't this beautiful, fully constructed, gorgeous talk of which I will feel proud. This is oh my goodness, this is where we're at right now, and I hope I can get that information across to you. And if only it all joined up and was really pretty, I'd be very happy, but we're not there yet. So these guys, we introduced a program logic for JavaScript in Popple 2012. And we hardly did anything. JavaScript is enormously complicated, and we'd done lots of work on separation logic for various forms of memory model, and in particular some quite bizarre memory models. And Gareth, who'd just finished a PhD thesis on DOM, said, aha, let's do JavaScript. And I can't think of any more complicated memory model than JavaScript. It's actually completely and utterly balmy idea. And all these years later, we're still doing it, and it's still a balmy idea, but actually it's quite fun. And for Popple 12, the only thing that we were doing was, what does it mean to reason about the emulated variable store, which is what's going on with the JavaScript. You emulate the variable store in the heap. There's lots of spaghetti to do with prototype inheritance, and what does it mean to get rid of the spaghetti, find abstractions, so that you can end up with axioms for assignment that look like axioms for assignment. An axiom of assignment is a very small thing. In this world, it depends on that derivation to get to that very small thing. And that was all Popple 12 was about. We hardly did anything to do with examples. We did a toy little form manipulation example, but it was very much us doing toy stuff. This talk is about trying to get away from those toy examples. For Popple 12, we introduced, we were using 3 things. One's the notion of negative resource that was very much very common in reasoning about concurrency, and we pulled that in to reasoning about JavaScript. In particular, this means in object L, I have a field X. It could be standing for a variable X with value, either a normal value or in this case nothing, meaning it's not there. So that negative thing of it's not there, which means you can start going looking around. It's not there, it's not there, it's not there, oops, it's over there. We're able to abstract away from that to end up with this abstraction, which is the only thing we really need to know about from the point of view of this talk. You have an object with its address. You have some fields that are not in there, and you have some fields that are in there with the value. So it's not describing the whole object, it's just describing certain fields, some in, some not in. When that vertical bar is not there, meaning that lot, i.e. things in. And just from a point of view of history, really, that in order to get this, we had to work with something that John Reynolds very much knew about, but sort of never quite grabbed, which is the notion of overlapping conjunction, which we were calling SEPish at the time. And I don't need to say any of that. I'm working with normal star of separation logic, because you build up the abstractions so that you can forget about that sort of thing. But and there's been work more recently on working, for example, with DAGs that has overlap. So in our case, we were doing overlap to do with prototype inheritance. And then we went sort of in a slightly different world, because what we were doing was saying, what's it mean to do a verification tool? In order to do a verification tool, we want to be able to trust the specifications we get out. And in particular at the time, Peter O'Hearn and gang were doing great work on here's millions of the lines of code, and we can verify it, but what does it mean to understand what it does? And so we were very much in that sort of what's it mean to trust the sort of thing that was going on. So we went into the world of what I'm calling JSCERT, which is mechanized operational semantics in COG. And we ended up asking the question, what does it mean to trust what we're doing? And we're doing it with people in Imperial and people in INRIA, and in particular those killer COG specialists are in INRIA. And from that, we can do lots of things. One of them being the program logic stuff, which I'm talking about today. And then there's lots of others. In particular, the French are very keen on flow analysis. Sergio is very keen on type systems and secure sublanguages. So this is sort of where it's where we were last year. And then just focusing down on the program logic part, this is what we're exploring in the program logic part. There's Diver, who's working on verification tool. She did some prototype last year and now is doing it properly for a thesis, as it were. There's, well, of course we want to build on top of what we've done. And there's extending the tiny stuff we did in POPL 12 to a higher order. And going to secure variants of JavaScript and working with what does it mean to say that something's secure in the logic. So from the point of view of this talk, I'm going to give one example here and one example here, and that's it. Of course they should have joined up, and when I wrote the abstract they were going to join up and be all really pretty, but life's not quite like that and it got hard. So I'm going to just keep them separate, but knowing that you guys know that they're orthogonal and will join up. And I'm not going to say anything about this, but I wanted to show you where it will go to, but it depends in some way on people's interest, you know. So we won't be doing everything, but we will be doing some of this. So all I'm doing is 2 examples, yeah? I say that because it might get a bit heavy. And the first is absolutely to do with Gareth Smith. And he's completely proud of this work because, for example, he said, in my 8 years, this is the first time I've got to real world code. So that's the sort of overriding message, that he's a very practical guy, and it's taken him a long way to get anywhere near the real code. So, 2048. I think people know about it. I was checking whether people knew about it a couple of days ago in my department, and somebody said, I can walk into the lab any time and at least 3 students will be working on this having a game. So, and it's so stupid, it isn't even that interesting a game. I mean, you'll either deadlock or you'll get the result at the tile, 2048, and in fact often it's very easy to get to 2048. So he was waxing lyrical about that. But basically, Gareth has done some of 2048. So in particular, let me show you, for those who don't know what it is, you've got a grid-like structure here. You've got tiles in the positions, and you can do something weird, which is flip the grid. So for example, I can flip the grid downwards so that that 2 goes there. I can then, with this 2 and this 2, I can merge them together to make 4. I can then flip down this way to get 16. No, 8, duh. And the aim of the game is to end up with a tile 2048. So you don't need to know about the game, but the point is that you've got this grid structure and a tiling structure. And other people will know better than me, but the point about JavaScript, there's certainly some good bits, there's certainly the whole lot. In fact, programmers find the sweet spots of what does it mean to combine OO and functional together. And depending on the different styles of problem that they're doing, there's different sweet spots, and some are more experts at some over the others. And we're going to, one thing we're wanting to do is try to grab at some of these sweet spots. And in particular, Gareth tells me that this is one version of sweet spot as exemplified by code from 2048. And I will hardly say anything about it, but let me just give a bit. So, you've got this grid constructor, so we're very much in OO land. And in OO land, we have the ability to construct a grid. It has size, and it's constructed by a 2-dimensional array. So you have a field called cells that starts off as an empty array and then turns into the array where the other arrays come off that are the columns of the grid. And this build method creates those columns depending on what the size is, starting off putting everything as null, and then you can start working with that structure. And then here's where the combination of OO with a function comes in. For each cell, you can call a function on that cell. So in particular, you've got callbacks. So basically, for any function, for every x coordinate, every y coordinate, you call that function using x, y, and the value of the tile that's sitting at that place. And here is the tile, and the tile has a position. This is an object with it has these fields x, y giving you the position, and also the value, and some other associated methods that we need to talk about today. So basically, you've got the grid with its notion of position, you've got tile with its notion of position, And the point of the program logic is to say these guys match when you're wanting them to match. And before going to the grid example, I'm going to do it on, I'm going to show the technique on in-place map that everybody knows. So we have a map function that's taking a function and a list. You're walking along the list, you're taking the elements of the list and replacing by the result of the function. And I'm going to call the body that does that this expression with the map subscript. And we have normal list predicates from the separation logic, where a predicate could be called as a function from basically addresses to assertions. So in the null case, we have no list. When we have a non-empty list, then now, because we're in this slightly different speak, you have an object at the address L where you have data and next field. Here's the data, here's the next field. So it's just a variant of normal separation logic. But this is not enough, because as in this map example, we're going to take a list, we're going to have some elements in the list perhaps satisfying an assertion, and then we're changing it via the function, and you want the elements of the list to satisfy a new assertion given by what the specification of the function is. So this is given by higher order list predicates, where, as well as what we had before, we also have a function going, in this case, from value to assertion. So basically, you're factoring in, you're incorporating assertions within this predicate, but you've got some function behavior going on, as I'll show you in a minute. So the list case is as before, and now here in the the null case is as before. In this case, we have the object as before, and for the particular data we have, we want to check that it satisfies this assertion. So by having functions here, you're hooking up the assertion with the particular values of the existential. This is no normal stuff in a non-normal setting. And we can give an in-place map specification like this. So first, the simple bit is saying, well, we have a list whose elements satisfies assertion P. And then afterwards, we have a list satisfying assertion Q. But where these P and Qs have come from the function that you happen to have brought in. And so that's the simple point, and then I have to explain P and this ASM. So P is this horrible looking thing. Yeah, it is horrible, and I'm not expecting you to know all the detail. But actually, if you start analysing it, it's not very horrible. And the tool's going to be able to cope with this. Because basically, that first line is saying where essentially the variable stack is, how to go about finding variables. So it's just saying, start at the lock address, and when you can't go there, start looking further up the list. You have the place where the parameters for that body of that map function is. And what are the parameters? Well, you need to know about the list you're working with, and that was defined on the, that matches what's going on here. So you need something pointing to that list you're working with. You need something pointing to the map function, because you're going to use it internally. And you need something pointing to the function that you're working with. So this is just OO land, it's just pointers to the place you go next. And here and here are giving you the function object, where you find the particular functions you need. So all this specification is really saying is here are the places where you find the information you need. And so, for example, this one is saying this is the address of the function object, just telling you where you find the body of the map function. You've got the scope object associated with the function, so you've got function closure, so here's the scope object. And for technical reasons to do with JavaScript, you need to keep track of the parameters. So here am I keeping track of the parameters. So that complicated thing actually isn't, it's just our game of, we're in this very syntactic world, all of us. And the other thing to explain is ASM. And so, for example, you've got the function that you're actually working with, this function here. The only bit you really need to know is that the data, the argument coming in is going to satisfy P, the assertion given by P, and the argument going out is satisfied by assertion going out. This is like the other one is just giving you the parameter to the function, and your scope's changed because of function closure. So this is all what's going on. You're following objects, working out where your functions are to then work with them. I want to emphasize something that's different from some people's work in this audience. So the absolute gurus of higher order separation logic reasoning are people like Derek and Honsat and Lars, and probably some others in the room, and excuse me if I haven't mentioned you. And what they are doing is a much more meaty higher order logic than we are. And in particular, they are factoring in assertions of this form. Oh, I can't remember. Okay. Assertions of this form.
Thank you.
Hello. Assertions of this form into the logic. And the reason why they're doing that is because they're wanting to capture how modules behave. What's going on with JavaScript is that you don't have module structure. Everything is done by functions and following functions. By the time you get to the next version of JavaScript, ECMAScript 6, you are going to deal with modules. But we're not going to go anywhere near that because we can't even do the basics yet. So what we have is a much simpler version of higher order logic, very much due to, if people know Billy Joel, it was his work, which is where it's enough to work with induction and step indexing rather than go full to that toppers of trees stuff that I find agonizing, but it's because it's clever, not because it's bad. Yeah. So we are simpler than that approach, but it's enough. Okay, back to the grid constructor, but all I'm going to say really is it's the same thing. Yeah, so we've done it for the in-place function, and now we're doing it for the same thing. We've got the grid constructor, we've got the tile constructor, and here are the grid assertions. And yes, again, excuse me, it's a mess. Yeah, we'll do better with syntax at some point. This assertion describes a grid object. And this assertion, so you've got the grid object at L. You've got a bunch of stuff. Remember that vertical bar and stuff there. It's grayed out because we don't need to talk about it. It's all the methods that can't be there because they're somewhere else. So it's just saying this is sort of the basic construct of the grid object. And we've got the notion of cells, size, and where to go to find the rest of the methods, such as these ones, including that build. Size is easy, and cells points to this array predicate. And this array, so this one here corresponds to this, which is why I did it in blue. the array has the size, and what happens with the array structure is you give it an I, you're thinking about that horizontal array, you give it the I, and now you're dealing with this other array. This other array is this bit. And then you give it a J telling you where you are down this bit, and at that point you're having to work with a tile at that position IJ. So even though position of tiles and position of grid in the two-dimensional array are different, this is how you hook them up. And this is what the logic is doing. It's giving you that ability to hook them up. And then we have a grid module assertion that's telling you where to find the appropriate methods, etc. This is sort of putting in some of that module structure that isn't there in JavaScript via these assertions. So then if we look at each shell, which if you remember, it went along each cell and did the callback function on the positions and the value that you get from the tile. Then we can do a specification of it, and yes, excuse me, again it's complicated, but everything is based on simple things. It's quite interesting. So basically we just did it in a simple invariant just to show you what's going on. And you need the array module, grid module, tile module. Yeah, I've not defined them. You need this grid thing that I was telling you about. And then you have the place where the parameters are. And the parameters were x, y, and the callback function. That callback function is here with that body. And so you need to know what that body is doing. You get to know it because it's in ASM. And in this simple case, I've grayed out everything you really need to look at. It's just saying the tile position structure is invariant. So the values are changing, but the tiles are not. And given that we're just in this simple grid example, all that we're doing is changing powers of 2, so you could start analysing a bit more, but there's not much to do of how the function's changing the argument, so I haven't put it in. So that's literally it, and that is my first example. And all that we've said is that we can build structure on top of the JavaScript programs that one has and prove these extra bits of information. Some of the normal typing information that you guys are very, very used to. And then some is not just normal type information, it's doing things like putting the position of the tile and the grid and make sure it's matching. Yeah. One more example. So, in particular, you don't need to remember anything from what's gone on before because I didn't manage to put the two bits together, bother it. But in particular, just remember that object structure, that's all you need. So, this is Gareth again. I mean, Gareth, very practical guy. The combination of over the years of us lot doing stuff has been amazing because he's so inspirational. And Thomas Wood is just starting, a new PhD student. So this was his MSc work and continuation of. So, just to motivate, why do we need to think about security for JavaScript? Well, I gather that this is a well-known webcomic, and they're making some daft comments about various forms of ridiculous sorting algorithms. And then you do mouse over text, and this is where usually the funny bits are. And in particular, this one says you can go to a web page where there's lots and lots of collections of sorting algorithms, and randomly you can pick one. And so I'm not sure if this is going to work here. Let me try it. Yeah. So this is it. And here's something to sort. So let's try and sort it. oops, that didn't work. But actually something hasn't worked, because in Imperial what happens, there's a window that pops up that says, hey, do you really, really want to do this? Press OK if you do, because you're getting random code off the web. Yeah. So that bit, I knew that bit had gone here. I tried it earlier. OK, that didn't work. Oops. That one looks better. That doesn't look very good. So you can have some fun doing this. So this is an extreme example. Why on earth would you trust that code on the web? It certainly doesn't give the right answer, but what on earth might it have done under the hood? Versus something like, here's Google Map, where you respect that's a respectable company, and everything in between. So what does it mean to get at security properties for JavaScript? I think it's essential. And some of you know this guy, Mark Miller. He went around a lot of the theory community a couple of years ago talking about his ideas of good programming practice. And a few people have begun to think about this in all their different ways of different forms of analysis. How can we capture not just some of his intuition, but the intuition of what does it mean for untrusted and trusted code to be sitting next to each other. And the systems guys, I think, have been doing it for years. So they've got this tool in Google based on Mark's work. And the idea is to be able to embed untrusted code in your website and have this sense of security. And that's a wishy-washy statement, but in Mark Miller land, that will mean some notion of object capability-based security, if you happen to know what that is. Basically, what Mark Miller insists on in order to play his programming techniques is the following things from an object-oriented language. You have unforgeable references. I don't think anyone's complaining about that. You can't do pointer arithmetic. You go to the place where you've been told to go. You can't go where you haven't been told to go. You've got some form of encapsulation. What that means in JavaScript is function closure. These two are just saying basically you can't find other ways of getting at the references you shouldn't be getting at. So you can't do global effects, for example. You can't create an object that is tied to all other objects. You can't do these sorts of daft things. But I think basically JavaScript satisfies most of this, especially if you go to ECMA 5 strict. It's satisfying most of this. You need a couple of little tweaks, which is what Mark Miller SES language is. It's secure ECMAScript. But for the point of view of this talk, it's enough to think of ECMA 5 strict. If you're not sure of these demarcations, it really doesn't matter. There's just ways of getting these sorts of properties within JavaScript. Now, so the Mark Miller philosophy is, with these assumptions, we can do nice programming and get some nice properties. He's going like this with it, but he's a skilled programmer, so they're not unreasonable. And let me try to explain what I mean by this tiniest example of what he calls memory. In the trusted world, you have these two objects, with this one pointing to this one. You've got some variable stack that I'm just writing informally like this. And you have a way to get to an untrusted function object. However, that's all you can do. That's the initial conditions, because we're saying you can't do, you can't forge references. So if you've got stuff from the web, it doesn't initially link to anything else, except for, in this case, via this evil. And what that means It's not possible, you haven't got a pointer directly to this. You also haven't got lots of pointers, a path. You haven't got a reachability thing to this. So that's the initial conditions. Now let's start working with this structure. So in particular, I'm going to do this evil and give it no arguments. JavaScript is robust with respect, if you've got no arguments there, but here's a function wanting an argument, it just gives a dummy argument. Undefined, I think, I'm not quite sure even. It gives something. So, so in this case, the properties up there with no pointers are working. But as soon as you give it, for example, A, this guy can start getting at this stuff. And in particular, it can delete arg.x, where arg is A, means you can directly delete something in here. You can also find y and follow the pointer to start traversing all around this memory. So right now, without doing things, there's no way that this untrusted code can function with this in a safe way, because there's too much fluidity in what the language can do. So what Mark does is have ways of protecting the structure on this side through what he terms membranes. And the idea, so you don't give A, it's up to you what you give, but you don't give A, you give something called protect A. And this calls a function that basically creates things that protects. And I've stylized that by, so when you evaluate this bit, it calls a function that creates one of these objects. And this object is called a protector function. And basically what it is, what happens is this guy gets the pointer to here. This guy has the pointer to here. And inside here, you've got methods protecting what's going on. So for one example is you're allowed to read and you're not allowed to delete. But you could have any form of stuff that you like here. This can evolve and adapt. But the point is to preserve, as this function is being called in this way, to preserve the fact that this type of pointer structure still can't happen. And I think intuitively one can see that one can be able to do that. But actually, what does it mean to start reasoning about it and start proving properties of this? I'm stopping just before 11.
Yeah.
And in particular, so it's subtle, so in the case of this x, you've just got a value here, so you're allowed to read it, and you're not allowed to delete it. But with this y, you've got a pointer. You're not allowed to follow that pointer directly. So what you do is this guy, when it's being asked to get at y, creates this protector box for the next object, for the y. And so you can't delete this one, because this protects this one, and you can't delete what's going on here, because this is protected here. And I haven't said in any way how a programmer would implement this. I've just said this is what it would be nice to happen. And the point is to understand and specify the behaviour of these things, and then a programmer can work out whether they've done the job well or not. So in order to do that, we definitely need the notion of forward pointer that we've always had in this normal separation logic stuff. Here's an object, here's the field of the object, it has value b. we also need some notion of back pointer. Now, what notion of back pointer should we have? In particular, certainly we would really like no bad things are allowed to happen to B. You're never going to, that gets too hard. But something that's easier is the positive statement that only this pointer is allowed to point to B, or in this trusted space, a set of these pointers can point to B, and that's it. And because of the unforgeability principle of references, you're not going to get any more unless you're quite careful about it. Yeah?
Can you explain why you need backwards pointers? Because in normal separation logic, forwards pointers are enough to give you complete control over it.
Let me,
Okay.
next slide.
Okay.
So basically I'm just getting to here and then I'm saying, now how do we do it? So for example, the intuition is that we need this sort of thing.
But I guess what I'm saying is the intuition.
Wait.
Sorry.
Can you then define it using forward pointers?
Okay.
Yeah? Which is your question.
Yeah.
No. Oops. The answer is no. Here it's broken. Please just stick with me and let me get through my example and then do it. But the intuition is that you have this idea of the set of things pointing to it, and never mind how it's defined, you're wanting this concept. Well, at least with this concept, I don't know whether you are wanting this concept, but with this concept, you can do the specification well after. And in particular, I'm showing you the interesting bit, which are these protector boxes. And the point is that with this protector box specification, you are able to say, regardless of what's trusted here and regardless of the code either side, you're going to be safe. And so this bit is the sort of crux of it. And what it says, so this protector Y is saying what the code inside here is doing to get at this blue box here, get at this extra blue box here. And what it's saying is, I need a blue protector predicate corresponding to the blue box. It has an identity address. It's pointing to A. A has, this is the set of things that can point to A. So this one knows the immediate things it's pointing to. And this is the sort of local police force. So things in here include PA, which is this one here. So it's these, it's these blue boxes. This membrane is the overarching police force. This one, so here, this is the same as this. It needn't be the same, i.e. you can have less of them here than in here. Here you've got X points to, A dot A, you've got object A, field Y, and it points to B. This just says that B is a pointer. I could have made that notation clearer for you. So if it's not a pointer, you don't care. It's a different case. It's an easier case. And you know the things directly pointing to B. This is all in our trusted world, so we know exactly what's going on. When you've done this protector function on for Y, meaning for that pointer there, what it's doing is creating that blue box. That blue box is here, and it just says at some identifier, that thing now points to B. It has the things directly pointing to B in there, and you've got the police state, which is the police state as before, plus the extra one to do with PB. You can always add police state, so I added it there. It's not essential there, but it is essential here. And inside this protector is that back pointer, but now updated, so it's the trusted stuff directly pointing to B plus the police state. Yeah? But that's all it is, i.e. it's nothing coming from here. So because of that, you can prove that, you can prove these crosses, that it can't happen because the only things that can happen, you've got this direct control of. Now, let me explain how to do it. So one way of doing backwards pointer is like this. And I think that was your question, Derek. That you can code up in this way. If you do that, frame is breaking. Because you can always frame on something else that isn't part of what's going on. So it's something much more, I'm going to go off piste a bit. It's something much more intuitive than that, much more resource focused than that. In particular, if you just think about a graph, here I've got X, so this will be in an object, I have an X, but I'm just going into separation logic. So I've got an X, I've got this stuff in my local heap, and let's put something else in. This is in the rest of the heap, not the bit that I intuitively think of as the local bit. Then actually, there's two pointer structures going on here. There's a pointer structure forwards, which is the normal thing on what we know. And then there's, you can think of it almost as a local backwards pointer structure at Y, backwardsly, what's it, UX and Z in this case. And if I write something like that, I can't, for example, star that on with something else, because this is global in the sense it's all the things pointing to Y. It's local in the sense I'm talking about Y and nothing else. So you've got this combination of local global stuff being done through that pointer. And that is the thing that's getting the power to do this stuff and making the framework. And so, did I say enough about that? Yeah. So in particular, I don't think I've necessarily got the best syntax for this. But what we have is at the top, we have a normal forwards thing, where it's just basically looking at the normal local heap. Here we've got a backwards thing that needs to work with the global heap. This is the global heap, this is the local heap, and this LS are all the backwards things that I want to point to. It's local from a backwards point of view rather than local from a forwards point of view. I can actually, I'm talking to the experts now, I can actually make that H much simpler. I've just got the set of things that I'm thinking of forwardsly, the set of things I'm thinking of backwardsly, and they have to be compatible with the global thing. Yeah? And that's gone very into Rust and Leno land that I never expected. Or another way I can perhaps do it, forget about the global, I've just got the two local things, but then the compatibility constraints become much more complicated. So with this global thing, it seems as if things are going much nicer. Still tweaking it all over the place. In this case, it's a very, very local thing. You've just got that L, you haven't got anything in the forwards direction. Now, what's going on with star? With star, this is one version of star, and this works. It works intuitively. You can think why it works. It's because you've got two locals and you can star them together. You've got this sort of property, so you've never got that clash going on. However, you're completely off. This star is not conservative with respect to separation logic. There's another star. Let me try to explain what that is. And I'm going specialist again because I've just seen a few faces. But how could I not? Excuse me, I've flipped those round. That's just stupid. I've just meant it hard. Just think about it intuitively. One has the notion of just a heap. This is the local part. This is the global part. And one intuitively has the idea, this is the local part, and I really know what's going on here, and I have permission to change it. Here, I've got the global part, I've got knowledge about the whole lot, but I don't have permission to change the whole lot. I only have permission to change that bit. Now, what happens in frame